Hello everyone. Today let's solve the problem number 239, sliding window maximum. So what the question states here, we are given an integer array nums. You can clearly see here. We are given an integer array nums and a window size k. Right. So here we are given an integer array nums and we have been given integer array k. Right. A sliding window of size k moves from left to right across the array. So here a sliding window of size k they have mentioned here, right? A sliding window of size k moves from left to right across the array. So a sliding window of size k moves from uh, left to right across the array. Here in this case we have been given k3, means we have to consider the three elements within the particular window. Means let me show you correctly. So first three elements we will consider this one, right? So the next three elements will be from 3 to this 3. Next three elements will be from -1 to 5. Next three elements will be from this one, -3 to 3. Next three elements will be from 5 to 6 until from the last element will be 3 6 7 last, right? So three elements we need to consider at a time. So that is what they have given. So they have given window size k here. K in this for this particular example they have given 3, right? So I hope this part is clear. A sliding window of size k moves from left to right across the array. At each move, return the maximum element in the current window. So at each move, what we need to do, we need to return the maximum element in the current window. Means here suppose the first this one in the first this one, what do we call, first window. So among 1 3 and -1, which is the maximum element? 3 here, right? So we need to consider 3. So same goes with next window is 3 -1 -3. Among 3 -1 and -3, again 3 is the maximum, right? That's what we need to consider. Next -1 -3 -5 we have the next window, right? So -1 -3 5. So 5 is the maximum. Next is -3 5 and 3. Again 5 is the maximum here. Now we have 5 3 6. This time 6 is this one maximum. Last one is 3 6 7. Among 3 6 7, 7 is maximum. So we need to consider the this element. So the element that we got here as I mean the output that we got here as, after considering the maximum element from each window, 3 3 5 6 7, right? 3 3 5 5 6 7. So which is equivalent to the output that they have given for the that they've given in the that they've given for the example one in the question, right? So I hope this part is completely clear. So this is what the approach is basically. This is what the approach is basically. For this, we will be making use of the what do we call, DQ, double-ended queue. Before discussing about the DQ, so let me read out the question once again. We are given an integer array nums and window size k. A sliding window of size k moves from left to right across the array. At each move, return the maximum element in the current window and also return an array of these maximums for each window position, right? So here, that's what we got here. So before moving on to the main approach part or the data structure that we'll be using for this particular question, right? So I just want to tell you, it's a simple thing. Either we can make use of the standard queue, either we can make use of the standard queue, or we can make use of the double-ended queue, or we can make use of the queue. Basically we will be going with the sliding window approach with the we can go with the sliding window approach with standard queue or the DQ. So let's make use of the DQ, right? So queue we have we'll be solving more problems on the stacks and queues, no worries. But let's make use of the DQ. So one main advantage of the DQ is that over this one standard queue is that we can either make use of the DQ with the queues or the stacks, right? Either we can make use of the DQ either with the queues or stacks. Means double-ended queue or the DQ, what is the advantages? We can add or remove the elements from either of the sides. Suppose this is the queue, uh, so we can add the elements from this side or we can add the elements from this side. Also we can pop or remove the elements from this side and we can remove the elements from this side as well. So that name itself states that DQ, right? Nothing but the double-ended queue, right? DQ or the double-ended queue basically, right? That is the biggest advantage. And one more thing, either we can perform stack operations or the queue operations while while we are making use of the DQ. Suppose we have something very strict constraints, right? Suppose we have very strict constraints. We have written the code in queue, right? We have written the code by making use of the queue, and we are getting the MLE, and we have to change the code entirely, right? So if we have made use of the standard queue, we have to uh, change the code entirely. Or if we made use of the DQ, we just have to go with the stack, and instead of suppose we have made use of the recursion, instead of the recursion we can just change that one to the iteration just to get rid of the MLE, right? So in these particular cases, DQ will be very handy, right? So instead of the standard queue for this particular problem, let's make use of the DQ, right? So we know the approach. We will go with every window, each window here, and we have to consider the maximum element in within the each window, right? So 131, 3 minus 1 minus 1. So we'll be considering each window. From the each window, we have to consider the maximum element. In this case, why we are considering three elements? Because we have been given k equals 3 for the first example. Suppose k was 4, we were considering the four elements in each window, right? I hope the question is completely clear. So here again, we will be making use of the double-ended queue to store the indices of elements in the window in decreasing order again. So this part is very important. So we'll be making use of the DQ. This we discussed to store the indices of the elements. Yeah, we have to store the indices of elements because each time we are going with particular window, right? So this is fine. In the window in decreasing order, we are storing the indices of elements in the decreasing order to access the max in big of one time. Big O of one time. Decreasing order means, so here 3 comes first, minus 1 and then minus 1, so that we get this element, the maximum element, in big of one time. So that is the reason we are storing the indices of elements in the window in decreasing order to access the maximum in big O of one time. Simple, right? So this itself we have to articulate in the form of code now. As we are completely familiar with the approach, this approach we need to articulate in the form of code. Right, before writing the code, I just want to discuss the complexities of the code that we'll be writing. Right, so here the time complexity of the code that we would be writing. So just give me a second here. So the time complexity of the code would be big of n. The time complexity of the code would be big of n because each element is added and removed from the DQ at most once. Each element is added or removed from the DQ at most once. So the time complexity would be big of n. And what would be the space complexity? Space complexity would be big of k because DQ holds at most k elements. DQ holds at most k elements, right? So the space complexity would be big of k. The time complexity would be big of n, and the space complexity would be big of k for the code that we'll be writing in the future. Right. So I hope the coding part is completely clear. I mean, sorry. I hope the complexities part is completely clear. As we are completely familiar with the approach and complexities, let's quickly write the code. Initially, we'll be making use of the length of the nums everywhere. So let me assign that one to some variable. So I'll just give here n equals nums dot length. This is fine. So the next step is we need the output array. We have to store the max of each window, right? So definitely we need the output array. So I'll just consider here result or res. I'll just give result completely. This is fine. Result equals, so new int of, let's consider n minus k plus 1. So this is fine. So the next step is we have to store the indices of useful elements in the window, right? So as we are making use of the DQ, we are storing the window in the, yeah, indices of the window in the decreasing order. So let's quickly create DQ here. DQ of here, in this case, it is integer, as we are going with the numbers. Integers is fine. This one, let me make use of the DQ itself. So or let me give this DQ. I don't want to type this one entirely again and again. So this will be new array DQ, right? New array DQ. Sorry, this is only QUE. So this is fine here also. So I have typed extra UE here. this is fine, array dq. So let me do one thing here. Yeah, syntax is fine. So next part is iteration. Next part is iteration. We have to like iterate through this one, right? Every element in the window, particular window. So first let me go with for int I equals 0 less than n I plus plus. So this is fine. So within the this one for loop, we have to remove the indices that are out of the current window from the front. Basically from the front we need to remove, right? So I can write the simple if condition here. If not of dq here dot is empty, this is fine, and dq dot peak first here, this one less than or equal to I minus k. Then within this if condition, let's make use of the poll first property that the dq provides. So here I'll just go with dq dot poll this one first. So this is fine. So let me come out of this one entirely. So after this one, let's do one thing. Let's remove the indices from back while current number is greater than num set those indices. Right. So here we need to remove the indices from back while current number is greater than num set those indices. Means we will check for individual elements in the queue. Right. So we need to keep the maximum element at the this one first, so that we can access that one maximum element from each window uh, at the this one at the time complexity big of 1, right? At the complexity big of 1 basically. So how can we articulate the same thing in the form of code here? While not of dq dot is empty here, and so here iterated value of the nums, if it is greater than or equal to nums of dq dot peak last here. So here what we will do within the while loop. So again, let me make use of dq dot poll last. So this is fine. I hope this part is completely clear, man. While loop. So this is fine. After while loop, what we will do, we'll add the current index. We have to add the current index to the queue. So let's make use of the offer last here. Let's make use of the offer last operation that the dq provides. So here I'll just go with dq dot offer last. So this one will be of I basically, right? So this is fine. So when we have processed at least k elements, we need to record the maximum for the current window. When we have processed at least k elements, then we need to record the maximum for the current window. Means here I can write in this way: if I greater than or equal to k minus 1, then uh, max is at the front of the dq. We know that one, we have discussed this one several times, right? So I can just write it in this way. I'm making use of the result variable to store, right? So yeah, this is fine. Result of I minus k plus 1 here, this will be nums of dq. So let's make use of the peak first, this one peak first operation that the dq provides, so that we can access the first element from the this one dq, right? From the queue, basically double-ended queue. So here max is always at the front of the dq, so we have to access the first element. So we are making use of the peak first property, which basically makes sense here in the line number 19, right? So this is it. Next, the final step is we have to return the result. Let's return the result quickly. So here I'll just go with return result. Right, so this is it for the code. Let me format the code once. So exactly whatever we discussed in the approach, we articulated the same thing in the form of code here, right? So very simple one. So here in this case, so basically this is hard problem. It's not as much. I think this is not the hard one. So this should have been the medium one basically. The last problem was the problem that we solved was basically it was hard. The code was lengthier as well, and it should be broken into many things, right? So many sub problems, and then we solved. So here in this case, it's somewhat easier compared to this one. So I think this should have been medium rather than the hard. So this is fine. So yeah, this is it for the code. Let's hit the run button. So I hope this works. Let's see. So yeah, here you can clearly see the sample test cases are getting passed. So let me hit the submit button quickly. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case, right? So I hope the solution part is completely clear. I hope the solution part is completely clear along with the approach and the complexities, right? For now, this is it. Thanks for watching, guys.